Началось? Звук? Должно быть очень все нормально, судя по настройкам. So today we're going to finish this chapter about associated primes. So essentially only one interesting statement is left, and then we're going to start a new chapter about integral extensions. So last time we finished with the following construction. Of course we assume that all modules in this chapter, all modules are Noetherian. So then we take a submodule n and some Noetherian module m, and we discuss the following. Can we decompose this into intersection of n1, nk, such that so associated primes of the m modular, say ni, this is just a prime ideal pi. So in this case we call submodule ni primary, pi primary if you want to be more explicit. And we want to also assume that all pi's are distinct. And we can always achieve that. We discussed this last time. Whenever we have, say, n1 and n2, it has the same associated prime, or the same primes p1 and p1. You take the intersection of n1 and n2, and instead of n1 and n2, consider this intersection. And you continue doing this until you achieve the situation where all these pi's are distinct. Okay, so we saw that such decompositions always exist for any Noetherian module and any submodule, and the question was how unique this decomposition is. So last time we saw one uniqueness result. We saw that these pi's that we have here, so this list of pi's, this is exactly the same thing as the set of the associated primes of the quotient m modulo n. So this is kind of, you can think about it kind of as a uniqueness result, because, well, at least these prime ideals are uniquely determined, because this is exactly the set of associated primes, and this is canonically computed, well, if you have m and n. Now, the next proposition is about, so I'm continuing to assume to have this situation. So I have this decomposition, so primary decompositions, where all pi's are distinct. So then I can formulate proposition as follows. So proposition, so if pi, the prime ideal that I consider, is minimal, so in other words we also call this isolated. So if this is minimal, then for the corresponding component ni, well, this is completely defined, so there is only one choice for this, and this is the same thing as the inverse of the iota pi of the n localized at pi, where iota is the localization map. So iota pi is the map from the m to the m localized at the prime ideal pi. Right, so we have localization. For the localization, we always have canonical map. And then inside this npi, we have submodule npi, and we need to take the preimage. So in other words, you can say that for the isolated primes, the primary components are exactly the saturations of the corresponding modules. So the saturation of the submodule n with respect to the prime ideal pi, or the corresponding multiplicative subset, which is complement to this prime ideal. Okay. Well, first of all, we use the fact that localization commutes with intersections. So if I want to understand localization NPI, well, I can as well, I know that this intersection, so I can as well say that this is intersection of the corresponding localizations. Okay, so this is inside. No, the ideal is still the same. So this is pi, and this is, well, there are two indices here, sorry. So there are two indices, n1, and then I localize that pi, and then there is nk, and I still localize this at pi. Is it clear that localizations commute with the intersections? Well, let's do this for 2. For 2, we have something like short exact sequence, say M1 intersect M2. This is embedded into M, and then this is mapped to the sum of two quotients. Right? This is short exact sequence, and then we just take a tensor product. So you can say that intersection commute with tensor product with any flat module. So in particular, it commutes with localization. Well, because you just take this, take a tensor product with a flat model, it stays exact on this side. So wait. Okay, so we have this we have this observation that we can compute the localization NPI at as this intersection. Now the next observation is that if we look at the associated primes of the M modular, say Nj, and you localize this at pi. So I claim that this is an empty set.
J not equal to I.
Yes, so J is not equal to I. And this follows from the two observations. So first observation is that Pj is not in the pi. Right? So since this pi that we consider is minimal, so this is if j is not equal to I, Pj is not inside pi. And then you can just compute the associated primes of the localization using the formula. Remember that for the localization, we know that the associated primes is the same thing as the intersection of the associated primes of this module, which is just Nj. And then you need to intersect with the spec of the localization of the ring. And in the spec of the localization of the ring, well, this will be prime ideals that's sitting inside pi. Right? So then inside pi, there are no, well, first of all, the associated primes of this thing without localization is just Pj, but Pj is not inside pi. So the associated primes of this localization is an empty set. And if this is an empty set, so if this is an empty set, we can say that the corresponding module is a zero module. So M pi is the same thing as the Nj localized at the pi. Okay, so this quotient module is 0, or the same thing, these two modules are the same. Well, now if you go back to this formula with the intersection, we see that in this intersection, all the summands we can just drop from the formula, well, because this summands just coincide with the module, right? So whenever j is not equal to I can as well just forget that there is such as modules in the intersection. So the conclusion is that the NPI is the same thing as the localization of the Ni at the pi.
Why do you say that MPI is equal to NJPI?
Well, the set of the associated primes here is empty set. So we know the property of the associated primes that the set of associated primes is empty if and only if the module is 0. So this module is a 0 module. So then I just use the exactness of the localization to move it inside. And so the key observation in my opinion is that in this intersection you can have you get only one term, because all other terms you can just drop because they coincide with the MPI. Okay, so we already get some formula for the corresponding localization of the NPI in terms of the irreducible components. Well, then the rest of the computation is just straightforward. If you want to consider pre-image under the localization map of the localization NPI, well, you plug in the previous formula into this formula. This is inverse image of the localization map, and then you have Ni localized at Pi. Well, and this gives you exactly the Ni. Okay, so I want to finish this with this chapter with several exercises. So in some sense these examples are also exercises, but I think it's quite elementary exercises. So I just want to demonstrate you that even we have this uniqueness result for minimal primes, in general the decomposition is very far from being unique, and in fact you can even get families of decompositions, even in very simple examples. So let's take R to be just a polynomial ring in one variable. Let's take module M to be direct sum of R plus R modulo X, or just a copy of the field K. The submodule that I want to decompose inside M is the zero submodule.
Is the quotient R by X?
Yes.
Okay.
No, this is just an ideal generated by X. So if you wish, you can write this as a copy of K. Yeah. So then I take the following modules. N1 is fixed, so this will be always just the second summand. So 0 plus the R modulo X. But for N2, I take the whole family, so I'm going to call this N2 alpha. This is going to depend on the parameter alpha, and this will be the following submodule. This will be submodule of pairs where I have some polynomial P inside the R, and the second thing is just some parameter alpha times P at the point 0. Or in other words, well, just consider P modulo ideal X. That's the same thing. Well, I consider module for such pairs. Well, I'm writing this as a set, but clearly you can check that this is a submodule, not just a subset. So here alpha could be any element of the basic field K. So of course I assume that K is a field. And then I have the following two claims. So the one is completely trivial. If I take intersection of N1 and N2 alpha, well, clearly this is 0 for any alpha. We'll just compare these two conditions. Well, if you have something in the first module, then the first component has to be equal to 0, P is 0, so the second component is 0. So this is a trivial observation. Again, the second observation is also trivial. It says that if I take the associated primes of the M modulo N1, well, this will be just a copy of the R. So the associated primes is very easy to compute in this case. Well, this is just a 0 ideal. So this is a set that consists of only one element, namely the 0 ideal. And then the last claim that I want to make in this example is that if you consider associate primes of the quotient M modulo N2 alpha, then this is again a set that has only one element, and this element is an ideal generated by the element X. Yeah, this doesn't depend on the alpha. So let me leave this as a little exercise. It's not hard. So essentially you can just understand this quotient explicitly and compute the associate primes. So then we see that what we have here, we satisfy the conditions of the theorem. So these two submodules, well, N1 and this family for any alpha, these are primary submodules because we have this. And this for any alpha, this gives a primary decomposition of the given submodule N. So we see that in this example, we have the whole family parameterized by the field of the primary decompositions. So this is one more example showing that primary decompositions in general are very far from being unique. We saw, of course, examples of this situation last time, but last time it was kind of just a finite set of examples. Here we have the full family. Oh, and I have another example of this kind. Again, maybe something that can be done on the seminars. We consider polynomial ring into two variables. Consider the same ideal that we studied on the seminar, y squared xy, two generators of this ideal. And then I claim that we can find this as an intersection of the ideal generated by y and also x plus alpha y. Again, as before, alpha is an element in the basic field K. So another family of decompositions. Something is wrong here. Something is. Wait a second. No. The second ideal is a little bit more complicated. So it has two generators. The first generator is y squared, and the second generator is x plus alpha y. Yeah, now I think this makes more sense. Okay. And the last proposition in this section and in this chapter, I'm going to leave the proof of this proposition as exercise, but I don't think this is very hard. It's quite straightforward. So if we assume that we have a shortest primary decomposition, so this intersection such that the associated primes of the quotients are all distinct primes. So this is shortest or minimal primary decomposition of some submodule of n sitting inside some module M. And then I assume that I have also S inside R, multiplicative subset, such that I have condition that S intersect with all such prime ideals Pi is not empty. So this is for, let's say, for I between 1 up to some R. So here I have this parameter K. Here I have parameter R, and I assume that R, of course, is less or equal than K. So if I have this condition for some prime ideals, I can just reorganize the order and say that for the first prime ideals, I have this condition. So for R ideals, I have this condition about the intersection. So then I have the following. If I look at the localization of the primary submodule N, this will be the intersection of the primary components. And this is the shortest primary decomposition of the localization of N in the localization of M, and of course over the localization of the ring. So proof of this thing is going to be an exercise. Okay, so next chapter 7 integral extensions. So definition. So if I have a situation where R is sitting inside S, so then we call this extension. So R inside S is an extension, and sometimes I'm going to use notation that I consider S over R. So this just means that I have ring R, and over this ring R have another ring S. So then an element, say alpha in the S is called integral over ring R if there is a monic polynomial say P, so with coefficients in R, such that P of alpha is equal to 0. It's very similar to the definition of the algebraic element if you consider the extension of fields. So the only condition that is new here is that the polynomial P has to be monic. It means just that the leading coefficient is 1. So it starts with the x to the n, some coefficient x to the n minus 1, and etc. So this is what it means to be integral for an element. Now, second part of the definition. An extension is called integral. So an extension S over R is integral. Well, as you can guess, if every element is integral, so if every element of S is integral over R. And part 3, this is just a slight generalization, a map between two rings, so F is going from R to S, is called integral if S is integral over the image of this map. So for example, if F is just an embedding, this is the tautological definition, but in general this is not an embedding, this is something new that we don't have in the part 1 or part 2. Okay. So we're going to start with the following proposition that gives us a characterization of integral elements. So the following are equivalent for an element. So first part, so alpha in the S is integral. Second condition, which is equivalent, is that alpha, where I join alpha to the ring R, and then this is a finite generate R module. So this is finite R module. Condition 3, well, R alpha sits inside some T, where T in the S is a subring So is subring finite over R. And condition 4, there is faithful module M finite, there is a faithful, I need to say R alpha module, faithful R alpha module M finite over R. Okay, so the proof of this is not very hard. So we're going to derive from 1, 2, from 2, 3, from 3, 4, and from 4 go back to 1. Well, do you see why 1 implies 2? So what's the system of generators?
The coefficients of unknown.
Yeah, powers of alpha. So if this is an integral element, right, so there is an equation of integral dependence, right? So we have some p, that is x to the n, da da da. Well, I'm not going to write coefficients, so maybe up to a0. So such that p of alpha is equal to 0, well then R alpha is generated by elements 1, da da da, up to alpha n to the minus 1. So this is a system of generators. So, and this is the proof of that 1 implies 2. Okay. How about 2 implies 3? Do you see how to prove this? It's actually even easier. Yeah. So in this case, to show that if you have 2, that there is such t, or you just take t to be this R alpha. Okay. Okay, so now 3 implies 4. How to show that 3 implies 4? Okay, I'm going to use this little pause to erase the blackboard. No, I think it's even easier. You don't need to take quotient by the annihilator. Well, in this case, we know that we have this module T with such properties. Right? We want to show that there is module M with some properties. What if I just take M to be equal to T? Well, that's a subring. In the subring, we have element 1. Right, so is faithful since 1 sits inside T. So 1 is not annihilated by anything. Okay, and finally, the last step, why 4 implies 1. So I have such a module. I want to derive that for this element alpha, there is an equation of integral dependence. Yeah, but by the leading coefficient is 1. So the argument you're saying works nicely for the extension of fields. Well, here the answer is Cayley-Hamilton theorem, where you consider this module M, and you consider operation multiplication of the element alpha. So remember when we discussed regular elements, I introduced notation mu alpha, which is just the notation for the multiplication of the element alpha. So I can do this since this is our alpha module. I can multiply by element alpha. So this is the finite faithful module. So it is actually, if I choose generators, I can associate the matrix to this multiplication and then apply Cayley-Hamilton. That's a 0. So multiplication by alpha is a 0 of its characteristic polynomial, and that starts with the leading coefficient being 1. So it starts with, if you choose the correct definition, it starts with the x to the n. So characteristic polynomial of this operation is okay, I don't know. Well, to be completely precise, I need to say I consider characteristic polynomial of the matrix A, right? I plug in this endomorphism and I get 0. So A is a matrix for some generators for this map. So this is equation of integral dependence. Okay, let's derive one little observation from this. Well, first of all, any finite extension is integral. And this follows more or less immediately, for example, by the property 3. So in this case, you just take t to be equal to the s. So any finite extension is integral. And from this, we can also derive the following, that algebra S over R is finite if and only if it is integral and of finite type. Okay, so remember that we defined algebra to be finite. If this is finite, so S is finite as an R module. So integral we will just defined, it's still on the blackboard. And finite type, well, it means that it's finitely generated as an algebra. So this means that S is of the form R. You adjoin several generators, and then perhaps you have some relations among these generators. So that's a finite type. Okay, so let's see what we really need to prove here. Well, the first sentence we already know. This follows from the part 3 of the previous proposition. Now, what else we know? So let's take an algebra. Well, let's go in one direction. So I'm going on to prove this second sentence. So in this direction, what do I know? Algebra is finite, right? Well, this is more or less triviality, because finite implies integral that we already know, right? And any finite is definitely of finite type. Well, because if it is finite as a module, you take these generators, so any element is linear combination. So and here we have not only linear combination, but say powers of generators. So definitely, if you take these generators of the module, it will be of this type. Is it clear what I'm saying? That any finite is also finite type? Okay, so any finite is integral and finite type. No, finite generated. So this direction is trivial. So now let's do the other direction. So now I know what I know, that S, it is given to me as the quotient of polynomial ring on several generators modulo some relations. And I know, for example, that all xi's are integral. Right, so this is for I between 1 up to the n. Right, so if this is the integral extension, any element is integral. So in particular, generators are integral. Well, and then you just consider induction by n. By induction on n, S is finite. Right, so for example, if you consider only one generator, right, so clearly R adjoin one element which is integral, it's a finite, again by the proposition. So then you consider what happens if you adjoin to the, well, if you adjoin the second generator. If you adjoin the second generator but using the previous ring, well, this is still finite. So then you add some relations, but if this was finite, this is still finite, even if you add relations, etc. So this is by induction on n. Well, you already know some examples of the integral extensions, for example, finite extensions of fields. So maybe let's do some examples. So example 0, algebraic, and in particular finite extensions of fields. So then but it's over a field. So in this case, R is a field, you can just divide by the leading coefficient. So then, of course, we can consider examples like this. You take Z, adjoin, say, square root of 2, and then consider this as an extension over Z. That is kind of typical finite extension. So that's an extension actually as a module. It has only two generators, 1 and square root of 2. This, of course, not fields, no. So this is 1 is not an example of kind of 0. Now, well, you can do something like this. So let's say this is even finite. Well, we can consider polynomial ring in one variable as an extension of the polynomial ring in the square of this variable. It's kind of a version of the previous example, but in this example you consider polynomials. Right, so again, what you're essentially doing, you kind of consider polynomial in one variable, and you add the square root of this variable. But it's also a nice way to write the same thing using generators x and x squared. Okay, how about, so again, this is finite. Not just integral, but even the finite extension. So 3. How about we consider Z? I adjoin 1/2 and consider this as an extension of Z. Is this an integral extension? And why not? Yeah, so the naive polynomial, of course, would be 2x minus 1, right? But 2x minus 1 is not monic. And of course, if you try to, well, this is not a proof that this is not an integral extension, right? It just shows that the naive polynomial doesn't work. So you need to show that there are no polynomials of any degree such that 1/2 is no monic polynomials of any degree such that 1/2 is not a root. But that's again not a very hard exercise in polynomials. So this is not integral. And finally, well, let me ask you, can you give me an example of, so all these examples, well, this is kind of what you already know. These two examples are not just integral extensions, these are finite extensions. So give me an example of an integral extension which is not finite. Say extension of the integers again.
Like you take z and extend it by square of all prime numbers.
You mean square roots?
Yes, square roots.
Yeah. So you can do this. So you join all the roots of the prime numbers such that say p is prime, and you consider this over z. So this is integral but not finite. Okay, definition. So let's fix an extension S over R. So part one of the definition. So R bar, so it's not a best notation, so sometimes people write also bar with an S here to indicate what extension do you use, but let me just assume that I understand what S is and use just notation R bar. So this is by definition all elements X in the ring S such that X is integral over R. So this is a set of all integral elements. And this is called the integral closure.
And one is S is just an extension?
Just an extension. So this is why I wanted to write something like S. So this integral closure of R inside an extension S. So, but let's assume that S is understood and use this shorter notation as just a bar. So this integral closure of R in the S. So 2, if R is equal to the R bar, then R is called integrally closed. Integrally closed in S. And 3, a domain R is called normal. And sometimes people also say integrally closed. But I prefer normal. So domain R is called normal if R is integrally closed in the Q of R. So this definition doesn't depend on any extension S. So this is just for domain R. Okay. So of course, the first question you probably want to ask about this definition, is this really a subring, so R bar? So we need to show that this is a subring. Of course, a naive approach where, for example, you take two elements, X and Y, you have equations of integral dependence, and you want to derive equation for the sum, and also want to derive equation for the product. Well, it is possible, but this is not the the best way to solve this problem. The best way is to prove the following proposition. So proposition with two parts. So first part, if you consider elements alpha that are alpha 1 that are alpha n in the S, which are integral. So these are integral. Integral over R. So then R, where you I join these elements is a finite R module. And from this we can derive part 2, that's saying that R bar is a subring. Okay, so the proof of the first part is again induction. Induction by n. So n is equal to 1. We know by our proposition that this is finite. Then consider element, say, so this is finite. Now let's consider situation where we already know that up to alpha k, this is finite. And I want to add one more element. So I consider alpha with the number k plus 1. Well, clearly this element is integral over this ring. Well, because even integral over R, over the subring, so it's integral over larger ring. So this is integral. And then I use again proposition. If this is integral over this ring, well, then this thing R, where I join alpha up to alpha k, and then I additionally join alpha k plus 1, is also integral. So, sorry, it's also finite. It's finite. So this is step of the induction. And finally, part 2. So we want to show that R bar is a subring. Well, let's take x and y in the R bar. So what I want to show that R bar is closed under taking sums and products. But this follows immediately by the observation that if you, well, these two elements are integral elements. So by part 1, I can say that R, where I join x and y, is finite, right? But then R of the product and R of the sum, this is subrings in this ring. So they are again finite. So this is the end of the proof. Okay, so next proposition. Now we have two extensions. So R is sitting inside S and S is sitting inside T. So these are extensions, and if I know that S over R and also T over S are integral, then the conclusion is that if I consider T over R, this is again integral. Okay, the transitivity of integral extensions. Okay, so let's prove this. Well, I take an element, say alpha, in the T. Right? So I want to show that any element alpha in the T is integral over R. So that's the goal of this proof. So what I know already, so I already know that there is an equation of the integral dependence with coefficients in S. So there is polynomial. So let me use variable x with coefficients in S, such that if I plug in alpha into this polynomial, I'll get 0. Okay, so maybe I need to write the coefficients of this equation. So maybe I need to write that p of x, this is x to the n, plus bn minus 1x to the n minus 1, and the last coefficient is b0. So let's call the coefficients of this equation b n minus 1 up to b0. So all these bi's are in S. So now I know that S is integral over R. So all these bi's are integral over R, and now I can, what I can do is I can use previous proposition and say that R b1 up to bn minus 1. So this is finite R module, right? So these elements bi in the S over R is integral. So this, all these bi's are integral over R. Okay, so now I consider R with all these b's as before, and I also want to add element alpha additionally. Well, clearly this element alpha is integral over this ring. So this module is again finite. So it's finite. So let me be more precise. This is finite R b1 up to bn minus 1 module. Well, I claim that from this it follows that if I consider R b1 up to bn minus 1 and then I join alpha, this is finite R module. Well, since this is finite as this module, but this module is also finite as an R module. And I think that's all we need to show, right? Since this is a finite module, again, we use our first proposition to conclude that alpha is an integral element. Okay.
I want to ask a question about integral closure. Can it be that integral closure contains less than the ring because
No, this is not possible. Every element in the R is in the R bar. Well, since you always have an equation x minus this element, equation of degree 1. So every element is integral of itself over the ring. Every element of R is integral over R. So corollary from this proposition. So as before, I consider some extension. So this is an extension. So then I claim that R bar is integrally closed in S. So if you do this operation twice, integral closure, you get the same answer. No, that's exactly saying that this is already integrally closed. So it's saying that if you consider integral closure, this is integrally closed, meaning that if you consider integral closure one more time, it doesn't change anything. So proof. Okay, so let alpha be integral over the integral closure, R bar. So what we have here, we have R always sitting inside R bar, and then we have R bar, and then I adjoin element alpha. So maybe to be precise, let's say alpha is an element in S. Alpha in S is an integral element over R bar. Well, this is an integral extension, right, by the definition of the R bar. And this is an integral extension, well, since I assume that alpha is integral over R bar. So then, by the proposition that we just proved, I can claim that the extension R bar alpha over R is integral again. Well, it means that any element here is integral over R, but in particular element alpha itself is integral over R. But if the alpha is integral over R, it belongs to the R bar. So then alpha is integral over R. Hence alpha is in the R bar, by definition of the R bar. So next proposition is very nice. It's so simple, does it require a proof. So take an extension which is integral. Also take an ideal I in the ring S. So this is ideal. Let's say that the J is the intersection of the R and I, so this is some ideal in the S. So then S modulo I is integral over R modulo J. And I claim this is completely trivial. You don't really need to prove this. You just take equation of integral dependence and consider this modulo ideal. Yeah, but you usually can understand what's really going on, because here you have two rings and here you have a ring and ideal. Yeah, the notation is the same, but you can understand what it means from the context. Okay, next proposition is a little bit more interesting. So let S over R be integral extension of domains. So in other words, I assume that S and R are two domains. There are no zero divisors in S and R. So then S is a field if and only if R is a field. Proof. So we need to go in two directions. First, let's suppose that R is a field. So this direction. R is a field. So let's take some element X, which is in the S, but also not equal to 0. So I want to show that any element in the S is invertible. Well, I already know that this is an integral extension, so there is an equation of integral dependence. So x to the n plus a1 x to the n minus 1 up to a n minus 1. So this is just the fact that this is integral extension. So all the coefficients AI, they are in the ring R. So let's take this to be equation of the lowest possible degree.
Shouldn't the last one be AN?
No,
Actually,
no. Yeah. Wait. I started at 0. Yeah, I think you're right. So this AN. No, that's not really important. Okay, so this equation of integral dependence of the lowest possible degree. So I claim that AN is not equal to 0. Well, what if this is equal to 0? Well, there is no this constant term. I can factor this as an x times polynomial of the lower degree n minus 1. This is in the domain, so x is not equal to 0. I can cancel this x. So this would be a contradiction with this condition. So this is lowest degree, hence the constant term is not equal to 0. But then actually we're done with the existence of the inverse of the x. I just can write the formula for the x inverse. This is minus 1 over an times x to the n minus 1, a2 x to the n minus 2, etc. up to an minus 1. And this is in the S. Right?
x minus 1 is equal to this, yeah?
Yeah, so this is equal. From the equation of the integral dependence and the fact that the last coefficient, so this coefficient is not equal to 0, well, I can just kind of write the formula for the x inverse. You can think about this as a, if I take this equation, multiply it by the x inverse, I'll get this formula. But anyway, so if I take this element, right, so this is an element in the S, since x is in the S, all the coefficients here are in the R. I assume that R is a field, so it makes sense to consider this thing. So if I just take this element and use this equation, I can conclude that actually product of this element and the x is 1. So this is why this is x inverse. So any non-zero element has an inverse. Okay, now let's go in the other direction. So here I know that S is a field. So S is a field. As before, let's take X in the ring R, which is not a zero element. I want to show that that there is an inverse. Well, first of all, I can consider this X as an element in the S. So X inverse lives as an element in the S, since S is a field. So the problem is to show that this X inverse is actually an element in the R. So then I'm done with this proof. Okay, but this is element in the ring S, and S is integral over R. So there is an equation for the integral dependence for this element X inverse. So I can write x to the minus m plus b1 x to the minus m plus 1 plus etc. bm. So all these coefficients bi are in the ring R. So this equation of the integral dependence for the x inverse, and I want to look at this equation and multiply this. So let's say this is star, and then I take star and multiply this star by the x to the power m minus 1. So if I do this, well, I'll get equation of the, well, I get something like this. X inverse is equal to the minus, so I'm moving all the other terms to the right hand side. So this will be b1 plus b2x plus etc. bmx to the m minus 1. And what's nice about the right hand side of this formula, this is clearly an element in R. All the coefficients are in R, and x is also in R. So corollary, which we immediately get from this proposition. So if we have S over R integral extension, and we take Q in the S prime and P as before intersection of the R and Q, then Q is maximal if and only if P is maximal. So the proof is just the combination of the previous two propositions. You consider, I don't know, maybe I write it like this. So I have an integral extension like this, and this is the extension of the domains. So I apply previous proposition. Well, because this is just an example of the pre-image of a prime ideal and the map of the rings. We know that in general, if you take prime ideal, you take pre-image, this is prime. So this is just the case where R is embedded into S, special case. Okay, so next section, I think this is 7.2. So by the way, if I haven't said this, this was section 7.1, and this is called integral dependence. So the next section is the integral extensions and localizations. Integral extensions So as usual in commutative algebra, if you have something, you want to understand how this behaves with respect to the localization. So here I have proposition that everything is nice. So S over R is integral extension. Now because S is already taken for the ring, I'm going to use notation U for the multiplicative subset. So U in R is a multiplicative subset. So then localization of the S at the U is integral over the localization of the R at the multiplicative set U. So this is integral extension. So of course notice that here you can think about this as localization of a ring, and this is localization of the algebra. Because U is not, actually in this case it doesn't really matter, because U sits inside R, R sits inside S, so you can as well think about this as localization of the ring S, so the same thing. Here there is no problem. Okay, maybe there is no space here for the proof. Okay, so proof. Let's take an element, some fraction x over u. So this is in the u inverse s. I want to show, of course, that this is integral. Well, x is integral, so for the x there is an equation of the integral dependence, x to the n plus a1 x to the n minus 1 plus etc. up to an. So this is equation for the integral dependence, so all the coefficients R in the ring R. Well, again, I take this equation star and I do the following operation. I multiply this by 1 over u to the n. And when I do this, I'll get the following equation: x over u to the n plus new coefficient will be a1 over u. Then this will be, I'll have x over u to the n minus 1, etc. Do the same computations, and the last coefficient is an over u to the n. So this is equal to 0. So take this equation, multiply this by 1 over u to the n, and get new equation. And this equation of the integral dependence for the x over u, well, since if you look at all these coefficients, ai over ui, well, for these coefficients you can say this is the localization of the ring, right? So u was in the multiplicative set u, so all the powers are in the u, so these fractions are exactly of the right form. Okay. So next proposition. So I have an integral extension as before. And the multiplicative set subset. So then I claim that if I take the localization of the integral closure, this will be the integral closure of the localization. So localization can be used with taking integral closure. Okay, so first of all, we already know something. So we know that if I consider localization of the integral closure, this is integral over the localization of R. So this is by the previous proposition, by this. So this is integral. So every element in this localization of the integral closure is integral, meaning that I automatically get inclusion in one direction. So localization of the R bar sits inside the bar of the localization. So this gives us inclusion in one direction, and really we only need to do the proof in the other direction. So let's take a fraction x over u in the integral closure of the localization. Well, since this is an integral closure of the localization, that's an integral element over this localization. So there is an equation of the integral dependence. So x over u to the n plus some coefficient. Well, this will be integral over the localization, so the coefficients are fractions. So let me write this as a1 u1. Now this is x over u to the n minus 1 plus etc. up to the last coefficient, which is an over some un. Okay. So I have such integral dependence. All the coefficients are here in the u inverse r. Now do the following trick. Take t to be the product of all these denominators. So this is a product of u1, u2 up to un. So all the denominators that you have in the coefficients. Again, this equation is equation star, and the computation you do is that you take star and multiply this on the u to the t raised to the power n. Now if you do this computation, then I claim that what you get is that from this equation you get that xt is integral over r. Well, just take this thing. For example, let's look at the leading term. Well, you get the cancellation of the u to the n and u to the n. So what's left is just product of x to the n times t to the n. So the leading coefficient is exactly xt to the n. So then if you do all other computations, then you just find the corresponding element in the t, right? Then you get the cancellation with this denominator, and then what you get, the coefficient will be just an element in the r. There will be no denominators. And you still get some powers always, well, in the t, well, one of these u's you're going to use to cancel, and what's left is power of t, which is n minus 1. So you get an equation of the integral dependence for the xt. So the last step is the following. You go back to the fraction x over u and just rewrite this fraction as the xt over ut, right? I can do this. T is in the u. So if I rewrite this fraction, well, I can see immediately that this is in the u inverse r bar. Right, so this is fraction where denominator is in the u and xt is in the r bar. And that's what we want to show, right? We started with the element in the right hand side and show that this actually belongs to the left hand side. So this gives us conclusion in that direction. So I'm calling this proposition, or I can as well call this corollary. Okay, let's call this proposition. R is a domain. So then the following are equivalent. So first, R is normal. Second, localization at prime ideals is normal. So this is for any p in the spec R. And 3, of course, is that localizations at all maximal ideals are normal. So this is normal for any m in the spec M R. Okay, do you see how to prove this? Well, there you should. This should remind you some when we discussed the stockwise properties, local properties. So, for example, you know that you can check exactness like this, but you can just combine what we know about exactness with what we do here. What if I just consider map like this, which is always injective. So I have condition 1, if and only if this is surjective, and being surjective I can check at stocks, prime or maximal. That's all. But it's kind of interesting that you can check being normal, which is defined kind of like a global property, but you can check this locally, which is maybe a little bit surprising. Okay, so that's all for today.